So today we're going to wrap up the lecture from last time on stochastic dynamic programming, and in particular the infinite horizon extension to it. And then we're going to move to the next topic, which is that of closed loop optimal control in continuous time, which should be a pretty interesting lecture, as you'll see. Now, going back to the discussion from last time, the place where we left it off is we define the extension of stochastic optimal control to an infinite horizon. What happened? I want to know about the joke.
I said 4 restaurants open on my...
4 restaurants. I hope that at least one of those is Italian. Is it? No. -5, so CA, you can. -5 points. Anyways, all right, so we set up the infinite horizon optimal control problem, infinite horizon MDP problem. And then we discussed how the notion of a Bellman equation extends to that setting in a specific form represented by the fixed point infinite horizon Bellman equation, whereby now the optimal value function, we talked how in an infinite horizon setting, typically people reason in terms of rewards as opposed to costs. So now the object we are trying to compute is not the optimal cost, but the optimal reward, also referred to as optimal value function. So the optimal value function satisfies a fixed point equation whereby V star x, the optimal value for the problem that starts at state x, is equal to the maximum overuse of the immediate reward plus the average optimal reward to go, where the summation over t x prime xu is essentially averaging the optimal value function from the perspective of the next stage with respect to the all possible realization of the state at the next stage, given that we are in state x and we choose control u. And then we saw that if you are interested not in the optimal value function, but in the value of a given policy pi, so basically how much reward a given policy pi accrues over an infinite horizon starting from state x, well, this quantity referred to as v subscript pi of x can be computed as a solution to the equation portrayed here, which in the case of a finite state space amounts to solving a linear system of equations into the components of the value function vector. Remember that v of x is the value for a specific state x, and if you have 10 possible states, then you will have 10 different values, one for each possible value of the state. Does it make sense? And then the additional twist that we introduced last time is, what if we introduce the notion of a Q function that conceptually takes on capture the concept of starting at x using control u and then using the optimal policy from the next stage onward? If that is the case, so if we reason in terms of the Q function, Q star function, then the Q star function actually satisfy an equation that is very similar to the Bellman equation, whereby the optimal Q function is equal to the reward, the current reward, plus the average of the maximum Q function maximized over U prime. We derived this equation last time, so I'm not going to go through it again. But the bottom line is that if you have an infinite horizon MDP, then we have an analog of the Bellman equation in the infinite horizon setting, which is represented by a fixed point equation, either for the value function or for the Q function. We discussed last time why the notion of a Q function is particularly useful in learning settings. We'll come back to it in 3-4 lectures. So now the next question is, how do we solve the fixed point equation? So this is an equation in which the unknown is the function v of x. We know r because we specified. We are in a setting whereby we assume that we know the transition probabilities, so we know R and T, but we don't know V star. So how do we solve for V star? Or how do we solve for the optimal policy? I mean, in general, you are interested in the value function, but most importantly, you are interested in the optimal policy because that's the object you use in order to control your system. So at a very high level, there are two settings that we're going to address in this class, and both are extremely important. The first setting, which is the setting of the remainder of this lecture, is the setting where we know the transition function T, it has been given to us, we know the reward function. So in this setting where all the problem data is known, the only unknown is the value function and the optimal policy, there are two broad classes of algorithms. One referred to as value iteration, and the other one referred to as policy iteration. It's important you familiarize with these two concepts because they become especially important as we move to the learning setting. Specifically, in the learning setting, some of the problem data is not assumed to be known. For example, we may not know or have direct access to the transition probabilities T. So how do we solve for the value function? And how do we solve for the optimal policy? There are essentially two types of methods. The first type is referred to as model-based. The idea is that you infer from data all the problem data, for example, the transition probabilities, and once you've done so, then you're back into this setting where all the problem data is known, and then you can use value iteration or policy iteration. Or you just go directly to the quantity that you care about, to the optimal value function and the optimal policy. Those methods are referred to as model-free. So in this class, we will cover both model-based and model-free methods. They have different pros and cons. We'll cover those in 2 to 3 weeks from now. But for now, we focus on the first setting, the one where all the problem data is known. And the algorithms, as we will see, are relatively simple conceptually. So let's start with the value iteration algorithm. The value iteration algorithm is quite intuitive. The idea is that you set up an iteration where you iteratively re-optimize the fixed point Bellman equation in a style that is very similar to the Bellman equation we saw in the discrete time setting. You start from an initial condition for the value function, maybe just a zero vector, so you assume that the value for each possible state is equal to 0. You apply one-step Bellman equation for many, many times, and then you hope that you will converge to something. It turns out that this algorithm is indeed guaranteed to converge to the optimal value function V star. So for any initial condition, the iterates, VKs, will converge to the optimal V star of X. If you have no clue about what the value function is, you can just start by assigning 0 to all possible states. Of course, if you have some guess about what the optimal value function is, you should use that guess. You're guaranteed to converge anyways, but of course, the convergence rate is much faster if you start from a good guess. So what is the intuition behind the value iteration? Remember that we are in an infinite horizon setting. So let's assume that you start at infinity. And then, so let's assume, okay, let me rephrase it. Let's assume that you, instead of having an infinite horizon problem, you have a finite horizon problem, but where the horizon is very, very long, like 3 trillion years. Then you start from 3 trillion years in the future, and then you start doing backward recursion many, many, many times until today. Well, that really approximates the infinite horizon setting. And that's the intuition behind the value iteration algorithms for the infinite horizon problem. And it turns out that in the stationary setting, once you apply the Bellman equation many, many times, you converge to a steady state solution, which is the solution to the fixed point equation that I showed before. Does it roughly make sense? Of course, there should be a proof to prove this statement. It's not entirely obvious. I'm just giving you the high-level intuition. Yeah?
So are you saying that this is like the essentially analogous to kind of like dynamic programming, but
Yeah.
just with like a very long.
Yeah, so we spent half an hour to explain the infinite horizon setting, but at the end of the day, we're still doing finite horizon computations, yes. But if you do it many, many times, then you're guaranteed to converge to the solution for the infinite horizon setting. Yep, that's exactly right. And of course, once you have computed the optimal value function, then you can backtrack the optimal control by just solving for the maximization over the use. And now you know V star, so actually this optimization problem can be solved.
You're in advance how many times do you have to repeat to guarantee that will actually convert?
No, unfortunately, it's asymptotic. We'll come with, I'll show you another algorithm that in some cases actually has a finite horizon convergence guarantees. So then you're raising a good point though. When do we stop? What is it? When do you stop value iteration? In a way, it's similar to the situation where we're doing gradient-based methods for optimization. So, for example, if the difference between the VK and VK plus 1 across all of the states is not too large, that could be a good termination criterion. Or maybe after an arbitrary number of iterations, say 2,000, just call it a day. So there are different ways to terminate the algorithm. There are, of course, a bunch of much more sophisticated analysis that also give you an error bound in terms of how much you might be far off the optimal value function after a certain number of steps. But in general, termination is not obvious. But you're guaranteed that if you do it many, many times, you converge to the value function, optimal value function. And there is an analog of it also for Q functions, is essentially taking the fixed point equation for the optimal Q function and then iterate. Analogous intuition. Policy iteration. I'm not spending too much time in value iteration and policy iteration because we will revisit these two algorithms through a learning-based lens, which is ultimately what we are mostly interested in this class. For now, I'm just giving you the overarching ideas and concepts and terminology. Policy iteration takes a different approach. Rather than operating in value space, that is optimizing over the value functions themselves, it operates in policy space that is optimized directly in the space of policies. Which kind of makes sense because at the end of the day, we're mostly interested in the optimal closed loop policy. The value function is more of an intermediary concept that allows us to compute the optimal policy. So the idea of a policy evaluation is as follows. It's still an iterative algorithm. So you start from an initial condition, and then you apply your insight into MDP and optimal control, and you try to come up with a better policy, and then you continue iterating until after you get to a good policy. Specifically, how does it work? Let's assume that you start from a given policy pi k. So here, k does not refer to the time stage, but is the iteration counter. So k stands for the kth iteration in the policy iteration algorithm. So you start from a policy pi k. Then what the policy iteration algorithm does is a two-step procedure where first we compute the value of the policy pi k for each possible state x by using the Bellman equation that allows you to derive the value for the value function for a given policy pi k. So you compute the v of pi k. This is the same equation I had in the previous slides. Note that here I'm computing the value associated with specific policies. So there is no optimization, there is no maximization with respect to u. So this equation, at least notionally, is easy to solve. We know R, we know the transition probabilities, this is just numbers. So this is just a linear equations in the value function v pi. So you could solve it as a large scale linear system. In the unknowns that are represented by the value of the policy when starting from each possible state x. X equal 1, x equal 2, and so on and so forth. Yeah?
On the right side of the first one, be pi k also? On the right side of the
Here you mean?
Yeah.
Yeah, absolutely. That's a typo.
K minus 1.
Here, no. So here, that's not a typo. Here is exactly what we had here. So if you're given a policy pi, the value, so the cumulative sum of rewards discounted with the discounting factor gamma, is given by solving the equation here.
How come it sort of looks like the right-hand side depending on the left-hand side, though? A little bit.
Yeah, this is a linear system of equations. So you would collect everything on the left-hand side. Here you have your constant terms, and then you will solve for the vector v of x is essentially a vector. Is v of 0, v of, assume that x can take on 4 values, 0, 1, 2, and 3. It will be v of 0, v of 1, v of 2, v of 3. Make sense? This makes it a bit more explicit. So after you've done that, then you have a big step. So the first step is referred to as policy evaluation, because we are evaluating the value associated to a given policy pi. The policy improvement step is where the magic happens. So now that we have computed the value for a given policy pi, we try to come up with a better policy. And to do so, we apply a one step of the Bellman equation. So we set the value, we set the control for the revised policy, P of k plus 1. This will be iteration k plus 1. As the control, the maximizes, since we're in the reward setting, the stage-wise reward, so the current reward, plus the reward starting from the next stage, approximated by v pi k. So basically, we take a one-step Bellman equation to try to improve the action that I should be taking at state x. So this is not the optimal action. The optimal action will be the one that you will be computing if you were to plug in v star, the optimal value function. But you use v pi k as a sort of placeholder that hopefully allows you to derive a better action. The optimal action is the one that you will compute if you were to use v star. We're not using v star because we know v star yet. We use a surrogate, which is vpk. So the key result, and of course there should be a proof here, is not entirely obvious, is that the value for the new policy is greater than or equal to the value for the previous policy. So actually you are getting into a policy that is better. Remember that we're in a reward setting, so the higher the value, the happier you are. And even better, the inequality is strict if pi k is suboptimal, is not the optimal policy. If you found the optimal policy, great. If you're not found the optimal policy, you know that the policy, the next iteration, is going to be better. So going back to the question from your colleague about finite time guarantees, assume that you have a finite number of states. So x can take on the value 0, 1, 2, 3, 4, and a finite number of controls. Do you think that this algorithm, knowing this property, do you think that this algorithm is going to converge in a finite number of steps? Yes, no? Because essentially, if you have a finite number of states and a finite number of controls, there are finitely many policies, different ways that you can permute the control with respect to all the different states. Since you know that at every step of this algorithm, you're always going to strictly improve the value of a given policy, there are so many times that you can improve the value until you reach the optimal value. So indeed, policy iteration converges a finite number of steps in the setting of fixed number of, a finite number of states and finite number of controls. Of course, what you should prove, and again, all these proofs are provided in great detail in the books from Bertsikas, is the monotonic improvement property we have here. So in a nutshell, with value iteration, we estimate the optimal value function, and we can compute the optimal policy through the Bellman equation once we know the optimal value function. In policy iteration, we start with a random policy, and we iteratively improve it until convergence to an optimal policy. Of course, all of this requires the model of NDP to be known. In particular, it assumes that we know the transition probabilities here. Otherwise, for example, you wouldn't be able to solve for the V pi k quantities. Yeah.
Explain again why intuitively the policy should improve each step.
Well, I mean, you are making essentially a more informed decision that exploit the structure of the problem, where you not only look at the immediate gains, but also the future gains. It is essentially a surrogate of what those future gains could look at. So it's not 100% clear what that necessarily brings to an improvement, but I think that intuitively stands to reason. Great. So this is all I want to say about the infinite horizon MDPs. We will revisit them at great length when we talk about learning-based control. So my main goal here was just to set the terminology for the infinite horizon instantiation of stochastic optimal control problems and really fix some foundational ideas in terms of how the Bellman equation applies into an infinite horizon setting and how we can solve for it through two main methodologies, namely value iteration and policy iteration. We'll come back to all of these in 3 weeks or so. So what we're going to do now is we go back to the deterministic setting, but we explore the complementary dimension whereby instead of reasoning in finite time, we reason in continuous time. So going back to our agenda, so we have discussed at length this branch. So finite horizon, closed loop optimal control through the lens of the Bellman equation and dynamic programming. We have looked at specific instantiations of the ideas of dynamic programming, including LQR. So now we are moving to the setting whereby now time is a continuous variable. So this is useful because sometimes problems are more naturally framed in continuous time, and sometimes the policies that are derived from the continuous time formulation are a bit cleaner and also a bit easier to implement. So we'll see. And so what we will derive is the continuous time extension of the dynamic programming equations referred to as Hamilton-Jacobi-Bellman and Hamilton-Jacobi-Isaacs equation. And then we're going to use those techniques to solve the two problems of importance. LQR in continuous time. This looks like all these classes, there's one problem we can solve is LQR. I mean, LQR is also a pedagogical, is important, is also a pedagogical tool. And then another very interesting class of problems related to reachability analysis. Actually, this is LQR is very important. Reachability analysis is also quite important. Is widely used, for example, to devise collision avoidance policies for autonomous cars or for airplanes and so on and so forth. Right, so the previous lecture, we focused on the discrete time setting. In this lecture, we focus on the continuous time setting. We will discuss how the dynamic programming approach leads to its continuous time counterpart, referred to as the Hamilton-Jacobi-Bellman equation and Hamilton-Isaacs equation. We'll use the Hamilton-Jacobi-Bellman equation to solve the LQR problem in continuous time. And then we'll use the Hamilton-Jacobi-Isaacs equations to address the reachability analysis problem that I will define later on. So just to make sure that we are on the same page. So far, this is the problem formulation we've been focusing on in the context of closed loop optimal control, discrete dynamics, and a discrete cost. Now we go back to the continuous time formulation. It is actually the one we started with when we were talking about direct optimization, when we were talking about open loop optimal control, where now the dynamics are written in terms of a differential equation, x dot equal f of xu. And the cost is now still an additive cost, but instead of a summation, we have an integral. So this lecture will be quite interesting. It's also quite deep, so stay attentive. And also, there will be some changes of notation across the lecture for very specific reasons that I will discuss, so be focused. The plus, though, is that actually this is a pretty interesting, all lectures, of course, are super interesting, but this one, personally, I find it particularly interesting. In particular, we're going to look at a more general setting that will become clear later while we do so. That is interesting in its own right and also quite kind of complementary to what we've done so far. Specifically, we now assume that in addition to everything I said so far, our dynamics are also influenced by a disturbance term dt. So when we were talking about discrete time stochastic formulation, d was just a random variable generated according to some probability distribution. Here, we're in a deterministic setting, but D encodes the notion of another player, think of it as nature, that is trying to interfere with our objectives. These are the so-called adversarial formulation for optimal control that are very useful to come up with control policies that are really robust. No matter what nature throws at you, within some limit, you're still guaranteed, if you use techniques that we're going to explain, to achieve your objectives. Of course, the price for it is that sometimes these policies can be quite conservative because they had to protect you from the worst case that nature can throw at you. But you see that all these things are complementary, right? So in many settings, you prefer a more stochastic formulation, average realization of what happens is fun enough with you. But, for example, when your life is at stake, probably you take a more pessimistic view of what could happen. So you're not happy anymore with just reasoning about averages. Actually, you want to protect yourself from the worst case. So that's what formulation is doing. Player one, we control u tau, is you. So you're controlling u to maximize j. So here is a little bit of a difference in objectives. So now J, even though it's written as J, plays the role of a reward. So you want to maximize J. You want to make J as large as possible. Think of it about your wealth. Player two, which use control dt, will aim to minimize J, subject to the joint system dynamics. So U and D are coupled through the joint system dynamics. So the evolution of the state depends on both U and D through the function f. And the cost G also depends on U and D. We'll see some examples later. But does this make sense? We have generalized the setting where now we have a disturbance, which is not just any disturbance, is actually an active player that is trying to damage you. One example that we will revisit later, and I also mentioned it before, is that of the homicidal chauffeur. So this is a person, so that's you. Player 1. And here there is a car. Well, I mean, my drawing skills are quite limited. Anyway, this is a car, okay? And so the pedestrian can move in any direction, but its speed is in general lower. So its top speed is in general lower than the top speed of the car. The car is faster than the pedestrian, but it has constraints on its motion. Particularly, a car cannot move laterally. That's why parking is annoying. If you can move laterally, I mean, for most cars, you cannot move laterally. So that's player 2. So UT is essentially the sequence of controls for your legs in order to get out of the way for the car. DT is the sequence of controls for the car in terms of throttle and steering to try to hit you. Now the question is, what is the set of joint states, so initial conditions for the pedestrian and initial condition for the car, so that you can survive no matter how hard the car is trying to hit you? Just to have a little bit of intuition, distance is not, it matters, but it's not the only thing that matters. Geometry and curvature also matter quite a bit. So if you want to save yourself, intuitively, what is the best way to initialize your position? So the car is here, and it's a top-down view. So this is the car. Okay, so here there are the wheels. And can maneuver in this plane, right? And can go backward. And you want to survive. Where should I drop you? Here? Or here? Here. Exactly. Exactly. So now you understand differential games. Because even though you are slower, since the car, it's faster, but it's also curvature constrained, what we'll end up doing, we'll start to constantly trying to circle around you, but you're smart enough to keep the car going around you. Of course, if you are unfortunately dropped here, most likely there is not much you can do. And no matter how you maneuver you, at some point, the car is going to hit you. Then the question is, how do we formulate all of that in a mathematical form so that we can actually find the controls U, D, and then the subset of the state space with a guarantee that if you start there, then nothing is going to happen to you. Why are these problem formulations useful? And then I'll get to you. Is, for example, for collision avoidance scenarios. Say that you want to develop a collision avoidance policy for an aircraft, and you want to be absolutely sure that other aircraft are not going to collide with you. I mean, in reality, the other aircraft most likely are not trying to kill you intentionally. But, you know, the other pilots maybe are distracted. So if you lack a better model for them, you just model them as adversarial. You know that if you really have a policy that allows you to save yourself under the worst possible action, then if the other pilot is distracted, is drunk, or maybe is really trying to hit you, then you're going to survive. Yeah?
From 0 to 0.
Oh, yes. So it turns out, and this will become clear later, that when we reason about closed-loop optimal control and continuous time, particularly with disturbances, these are problems referred to as differential games. They're games because there are two players, differential because the actions between the two players are constrained by the differential dynamics. In those settings, we like to think about the final time as 0 and the initial time, t0, as some negative time in the past. So view of t0 as -5, -6. This is really notation, and this is a typical notation used in the differential game literature. So it's really notation. There is nothing deeper here. But it's good that you pointed out. So for this lecture, the final time will be denoted by 0. So the terminal condition will be at 0. And we start in the past. Yeah?
Use this formulation to model stochastic environments. Why do we assume that the stochastic element is an adversary? For instance, in the example of the pilots. Couldn't a pilot be constructed in a way that goes farther away from us and therefore these are closer?
Yeah, I mean, this is just an adversarial formulation and the problem remains deterministic, so there is no stochasticity here. But you could also consider a stochastic formulation. Actually, ACAS-X, which is the next generation collision avoidance system, is built upon a stochastic formulation. And then, of course, you can capture some notion of adversarial behavior through the probability distribution that defines the realization of the random variable. These are different modeling choices. What I'm telling you is I'm giving you a menu, I mean, that's the point of this class, of different control methodologies and how to solve for them. But then, I mean, you're still the agentic agent that has to decide what to do, at least for the foreseeable future. Now, what interesting part, and here is when you have to apply your brain, is the problem, as described here, is not fully specified. Meaning, what type of information does player 2 have access to in order to respond to what you do? And there are a few formulations. The most intuitive one, but also a very bad one, is that I, as player 1, declare my full controlled sequence from time t0 all the way to the final time 0. Player 2 gets to see that, and then it optimizes its own optimal control sequence tt. Of course, this gives an enormous advantage to player 2 because it knows exactly what you're going to do between now and the final time. So this formulation typically makes the problem very simple because essentially the nested optimization between what the player does and the player 1 gets very easily decoupled. So you just look at all possible control actions that you could entail, and then I look how to optimally respond to them, and then I solve the optimization problem and done. Computationally cheap, but very unrealistic, very conservative, because you give an enormous advantage to the other player. The one we look into is a bit more sophisticated. So here, the player 2 gets to see what player 1 has done up until now. So it does not have an anticipatory skill of also seeing what you will be doing in the future. So it's a constant game between player 1 and player 2, that player 1 makes a choice, player 2 see that, and then they keep iterating in closed loop. Does it make sense? It's a little bit of a difference, but it's very profound. So the other agent, meaning player 2, acts based on state and control trajectory up to current time. Note, and the notation is that the set of strategies we look at are those strategies whereby we get to see u from time t0 up to the current time. Note the player 2 still has a little bit of advantage because it gets to see first what you do now and then a reply. Think about chess. I mean, usually white has an advantage because it moves first. So here, player 2 still has an advantage because at the current time t, you, player 1, make a move, and then I make my move. So I get to react. So actually, it's an inverse of chess, actually. So does it make sense? So this is the class of strategies we're going to focus on. Those that do not anticipate, which of course will be infeasible in practice, what the player 1 will do. So it's much closer to the type of operations you will see in practice. Any questions here? This is important. So if you have questions on this part. Okay, so if you have studied game theory, this is game theory on steroids. Because now there is a game aspect, but now you also have to think about the differential evolution of the dynamics, which makes the problem even more interesting because now there are geometric considerations you have to consider and so on. So the problem we want to solve then is as follows. We want to solve a minimax problem whereby the player one will attempt to maximize its outcome. Again, here we're in a setting where we view J as a reward. So you are player one, and you try to optimize your outcome. And player two will aim to minimize it, subject to the system dynamics F. So we want to find a U that makes the cost as high as possible under the most damaging disturbance D. Make sense? Yeah.
Might be getting into the semantics a little bit, but I'm curious, on the prior slide, you said that player two has the advantage. I'm struggling to see how player two would have the advantage when player one would be the one moving first in this structure.
Because essentially, I get to see what you do, right? And so if I know, for example, say that, for example, there are two cars. So this is player one, and this is player two. In a dynamic situation, say that player two wants to hit you. So, and you're player two. So say that you know that at time t, player one is going to move in this direction. This is a very useful information to you because you know that the action in these directions are not useful to you to damage player one. Actually, going this direction is advantageous. So you see how having access to what the other person is going to do basically allows you to rule out actions that are not going to be maximally damaging and instead focus on the ones that are maximally damaging. Does it make sense?
Are we solving for the worst disturbances or the optimal control?
Both. Yeah, that's why it's a minimax term. We want to essentially you're solving, I mean, at the end of the day, you care about you. But in doing so, you solve simultaneously with respect to both the optimal disturbance and the optimal control. So you try to find the U that makes the cost, as I said, as high as possible under the worst possible disturbance T. And you'll compute both of them. Of course, in practice, unless you take the role of player two, you're going to use the control U.
What's the notation? Gamma of U.
Yeah, so this is an abstract notation that says that we pick that is only those disturbance D that are not anticipative. So they can only react to what player one has done up until now. So it doesn't have, is what I was saying before, doesn't have access to what player one will do in the future.
The time history of player two, just
Yeah.
not at the like instantaneous.
That's right. So it's only an instantaneous advantage. Great. So that said, so the problem formulation here is quite sophisticated. Yeah.
Already, but why is the player one with the control U trying to maximize cost instead of minimize it?
No, so what I said is that in this specific setting, don't view G as a cost, view G as a reward.
Oh.
It's just terminology. So here, there is nothing deep here. So we are in a reward setting, but I'm using a J notation because unfortunately that's what the community uses.
Can we get a switch around like min and max, like find the minimum possible disturbance we get and then find a control that would like, given that disturbance, be most optimal?
No, actually, to give the advantage to play, so the fact that we're defining problem as a minimax with the disturbance as the outer optimizer is not by chance. This is exactly what gives the disturbance the advantage with respect to what the controller is doing.
I guess advantage.
Yeah, by placing it as an outer minimizer. That's right. Okay, so all great questions. So now, yes.
You want to have the same advantage just after G, please?
Yeah, so that's why the advantage is only instantaneous.
Okay.
It's a slight advantage.
Okay, but even at the beginning, doesn't P1 as an advantage knowing already the same advantage knowing already a state of P to use this the advantage to do that by knowing the state of P1?
Well, I think this business is best interpreted when you are at the general time t, and so you have some history of x p2 tau and x1 1 tau. So in this, say that you're just a general time t, having access to the information including time t, basically, strictly speaking, you have more information, right? Because you had additional bit of information at time t, and having more information is always more useful. Does it make sense? In general, more information is better than less information, so we can also justify it in that way. Great, all right, so how do we solve this problem? As usual, dynamic programming and principle of optimality. So the solution is as follows. We decompose the objective into two pieces: immediate reward plus reward to go. And remember from when we were talking about the principle of optimality that there is no loss in optimality if we restrict the search over the optimal controlled signals to only those controlled signals that result from the concatenation of optimal tails and then immediate rewards. So this is represented notionally by the drawing here, where I'm showing that if I give you the optimal solution for the tail problem, starting at time t plus t, a state xt plus delta t, you don't need to reason about controlled sequences to do something else, starting from point B3 or point B2 or point B1. You just concatenate the initial segment with the optimal tails, and you just compare the three controlled sequences that arise from these concatenations. So here I'm enforcing the principle of optimality in this decomposition of the cost. So here I'm not doing anything new. I'm really applying the principle of optimality in the same shape and form that we discussed a few lectures ago. So the point is that the problem here, which is the original formulation, h of x here as usual is the terminal cost, can be rewritten as the cost whereby I concatenate optimal tails with, in a way, one-step transition. So view basically this integral between t and plus delta t as a very short transition into the new time. So if you have fully grasped the principle of optimality, then this should be quite clear. If this doesn't look quite clear, it means that you haven't internalized yet the principle of optimality, so try to do a little bit more thinking about it. As I said a couple of lectures ago, the principle of optimality is such that when you see it the first time, you think it's obvious. After a while, it becomes very confusing. And after a little while, then it becomes obvious again. So when I say it, it's obvious to me, but there was a time where it was not so obvious to me. So what I'm trying to say, it takes a bit of time for you to really internalize it. Anyway, so assuming that we buy this step where we enforce the principle of optimality, so we just say that we look at control and disturbance sequences that are the results of the concatenation of optimal tails and a first bit of control between time t and t plus delta t, how we can massage this expression into something that leads me to something that is computable. So view delta t as a small time increment. By the way, this stuff mathematically is very complicated. So if you were to do it super, super cleanly, it would be a bit complicated. Here I'm just giving you the main intuition. This is probably one of the most complex concepts in optimal control. So the integral can be approximated as a g times delta t. So over a very, very small interval delta t, you can view the function g almost take constant value. So the integral is simply equal to the integrand time the time difference delta t. xt plus delta t can be written according to one-step Euler discretization as xt plus delta t f of x ud. I mean, we have done this many, many times. Which means that we can approximate the optimal cost to go from a time t plus delta t. I'll rewrite it here with a first order Taylor series approximation, whereby this becomes j of xt t plus gradient of j with respect to x times x of t plus delta t minus x of t. But this is equal to delta t f of x ud plus partial derivative of j with respect to t times delta t. So this is a simple step. Here, there is the crux of the problem. The most difficult thing to swallow in this entire lecture. So we have jj, so nothing new here. We have approximated the integral with just this quantity that we have here. We have substituted j of xt plus delta t, comma d plus delta t with its Taylor series expansion. Okay, so we have it here. But now the part that is tricky is that at this instantaneous scale. So now I have to remove u and d as a function of time over a continuous interval. Now d and u are evaluated exactly at the time t. So at this instantaneous scale, the disturbance is not choosing a whole trajectory anymore. It is choosing a reaction to the current control. So the nested structure changes from the outer player picking a function anticipating the optimal response to, at each instant, one player moves and the other reacts. So this becomes closer to chess, actually. So that's why we swap the order between min and max to preserve the advantage with respect to the disturbance. That's a part that is hard to swallow. It would require a much deeper proof. But the idea is that essentially we're trying to be consistent with our assumption that player 2 is the one that has the advantage. You give the control, and then the disturbance reacts optimally. And so the problem changes from min-max to max-min. So this is not entirely obvious, and I don't want to spend too much time on it because otherwise there will be an entire lecture on it. So I'm trying to give you as much intuition as possible. Here it might be a little bit cloudy what is happening. But the point being is that in order to be consistent with the fact that player 2 has an advantage, we have, when the problem boils down to instantaneous optimization, swap the notion of a minimum, maximum, maximum, minimum. So this is the hardest part to swallow. So it's a little bit of a step where you have to trust your instructor. But at least trust me in the sense that what we're doing here is try to be consistent with the assumption that the player 2 has the advantage. So the idea is that we are player 1, we fix u, and then d gets to choose the possible best response. And then you try to pick the u such that for that u, d has the less damaging response. But player 2 has an advantage because it gets to see what you do. Okay, so assuming we agree for this step, and from now on, actually, the lecture will be downhill. So it's uphill because the formulation of differential games is a little bit complicated because we have this business of non-anticipatory strategies that is relatively natural but not straightforward. It gets to the peak where this swapping between min-max and max-min is a bit, is deep as a concept, but then it gets downhill from now on. Yep.
Sorry, so why couldn't we write max-min since the beginning?
Because here, this min-max and this max-min has a bit of different interpretation. Here, we're doing nested optimization over the space of controlled sequences. Here, we're doing nested optimization over space of instantaneous control. So within this terminology, actually it turns out that to give the disturbance an advantage, it has to be part of the outer approximation. That's the part where it can be understood, but it would require a bit of a deeper discussion to be super rigorous. So that's what I'm saying. So it's a little bit of one of the few parts in the class where you have to trust your instructor. The most important thing, though, is that you understand the problem formulation and then you understand the final algorithm that we're going to derive. That's the most important thing. Here I'm just providing a little bit of intuition about where that algorithm is coming from. The specific steps are not so essential. Anyway, assuming we agree on this, then we arrive here. So J does not depend on U, so I can bring and D, so I can bring it out of the optimization. So these two terms cancel. Great. Then I can also cancel these terms delta T. Okay, and then I get to the celebrated Hamilton-Jacobi-Isaacs equation. So the optimal value function J is the solution to a partial differential equation. That seems like bad news. Partial differential equations typically are hard to solve. And so basically, if you want to find the optimal value function J, you have to solve the partial differential equation because you're taking the derivative with respect to both time and state. And the solution of this partial differential equation on top of it has a max-min problem embedded in it. So looks ugly, and actually it's not particularly pretty. But there are solution algorithms to solve this partial differential equation. We'll get to those later. But at least now you have a mathematical tool that allows to solve for the value function. And once you have the value function J, then you get your optimal control U by just doing an Rmax of all this quantity here. Of course, a partial differential equation, as any differential equation, needs to have a boundary condition, which is represented by your terminal cost. So I'll come back to this later, but first, I want to go back to the setting of standard optimal control when we do not have the disturbance. So we could have done the same thing, and it would have been even simpler. In that case, you get to the continuous time formulation of the Bellman equation, which is still, we don't have D anymore because we have removed the disturbance. So we are again in a setting where the dynamics are simply x dot equal f of xu. But now we're in continuous time. So this is the continuous time extension to the Bellman equation. It is still a partial differential equation. You take derivatives with respect to t and x. Again, you don't have the d's because here we're assuming that there is no disturbance. But here, at least I can give you an intuition about this equation represents. And then when I give you the intuition, you say, oh, but this actually is quite obvious. Specifically, let's rewrite the Hamilton-Jacobi-Bellman. So Hamilton-Jacobi-Bellman is when we don't have a player 2. Hamilton-Jacobi-Isaacs is when we have a player 2. So let me rewrite this equation as minus partial derivative of j with respect to t equal minimum over u of g of x u t plus partial derivative of j with respect to x of f of x u t. So if you look at this, doesn't look like the Bellman equation in discrete time? Sort of. On the right-hand side, you have the minimization over U, like in a Bellman equation in discrete time. And then inside, you have the immediate reward, or immediate cost, depends on how you interpret this stuff. So let's interpret this as now a cost. I told you that there's going to be a little bit of a shift in terminology. So that's now why we're minimizing over U, because we want to make the cost as small as possible. And this is the cost to go. And essentially it's telling you how the cost to go changes as you are moving your state one step ahead in the direction of your dynamics. So what is, and this is the partial derivative with respect to t, is the time rate of change of your optimal cost to go. So what this equation is telling you is that minus the time rate of change of the optimal cost to go is equal to the minimum over U of the immediate cost plus how your cost will be changing when choosing the control U, the state will move into a new state. Of course, you're not moving into a new state arbitrarily. You're moving into the new state following the dynamics. That's why the derivative is taking along your dynamics. So in continuous time, the Bellman equation takes the notion of a time rate of change of your cost function. While in discrete time, it was a discrete change across iterations. Does it shed a bit of light about where this is coming from? So why there is a minus? Well, we are now in a situation whereby J is interpreted as a cost. We try to minimize the cost. So as the horizon shrinks, there is less cost that you're going to accumulate until the end of time. And so your cost is going to decrease as you move forward in time. So it makes sense that there is a minus. Just trying to give you guys as much intuition that I didn't get when these results were presented to me, and I was utterly confused about where all of this was coming from. So all I'm saying here is that you shouldn't be too scared, at least from the Hamilton-Jacobi-Bellman equation. It's really very similar to the discrete time Bellman equation. But now, since we're in continuous time, we reason in terms of time change of rates of change of quantities in time, and with respect to how we're moving our dynamics, our state around according to our dynamics. In the adversarial setting, the intuition is a bit more complicated. Yeah?
So kind of saying basically you're trying to select U to ensure there's no change in the cost function? Like
No. Why not change in the cost?
Like, it seems like you're trying to select U so that you're like...
No, you want to make the rate in terms of time of change as large as possible so that you decrease the cost as much as possible. That's why you're minimizing the U. Okay, so any questions here? So main point is that we set up the optimal control problem in continuous time, actually in a more general version where we also consider the possibility of a second player that is trying to tamper with our objectives. We discussed how we had to place some assumptions in terms of how the player 2 can select its decisions. We argue how a good model is to assume that the player 2 is restricted to take actions that are not anticipatory, so it can only get to see what you've done so far, including the current time. That gives a slight advantage to player 2, which is captured by the specific formulation of the problem, where we do a min-max. Then, given that formulation, we invoked arguments from the principle of optimality to break down the problem into the solution of a problem whereby we concatenate current decisions with optimal decisions. Using that insight, then using a first order approximations with a little bit of magic and proof by authority, where I tell you it's true and you are not allowed to counter-argue. We derive an equation that is eventually what we care about, which is the Hamilton-Jacobi-Isaacs equation for the differential gain formulation of the problem, and the Hamilton-Jacobi-Bellman equation for the more standard version of the problem where there is no player 2. And for the Hamilton-Jacobi-Bellman equation, I gave you a little bit of intuition showcasing that even though the equation looks ugly, and it is ugly, but it does have some intuition, particularly in terms of embodying the notion of the discrete time Bellman equation, but in terms of rate of change. That's basically what you should internalize from here. If you want to get be deeper about this topic, as I said, it gets mathematically quite involved. Then I provided some references in the earlier here. These couple of papers go in much greater detail about these derivations. Great. So now we have all of these tools. Let's start applying these tools first to LQR and later, meaning Monday, to a class of problems that is very cool, referred to as reachability problems. So next time, we'll wrap up this lecture with an application to reachability problems, and then we'll move to MPC. Yeah.
In this model, player 2 can see the future action of player 1, but can he...
Cannot see it, cannot see it.
Right, yeah. But can you assume what, can you see kind of prediction based on what makes more sense?
No, we're in a fully deterministic setting, so there is no notion of stochastic prediction. Yeah. There are other formulations, but basically you can have a probabilistic prediction of what player 1 could do, but that's not part of this formulation.
Okay, so it's only formed on the state, current state, player 1.
Well, and history, yeah. All right, so let's apply now this stuff to LQR. So turns out that the 15th version of LQR we're going to see in this class is the one in continuous time. So now the dynamics are still linear, time varying, but they are given by differential equations as opposed to the discrete time equation. The cost is quadratic, but instead of having a summation, now you have an integral. Same intuition about the parameters for LQR problem. Q penalizes deviation with respect to the state. R penalizes control effort, assumed to be positive definite. T0 and TF specified, and there are no constraints on the state and the control. So, can you solve LQR by using the Hamilton-Jacobi-Bellman equation? Yes, you can. I'm not going to do the full derivation. It's not particularly insightful. For those of you that are interested, though, the way that it would work is as follows. So we know from the discrete time formulation of LQR that the optimal cost to go is a quadratic in the state. So you start with an ansatz. That's how oftentimes you solve partial differential equation. You start with an ansatz, which is basically the cool mathematical term for a guess. Right? So you start with a guess that your optimal cost to go is a quadratic for some matrix V that you do not know. That's a guess. You plug it into the partial differential equation, and then you see if there are some conditions on V that make the partial differential equation satisfied. So you do a bunch of boring algebraic manipulations, and you'll see that if V is chosen as the solution of this differential equation, where everything is known, so we know Q, we know B, we know A, and then we have the boundary condition that V at the final time is equal to H. So if V is solved according to this differential equation, referred to as the continuous time Riccati equation, then the partial differential equation, the Hamilton-Jacobi-Bellman partial differential equation is solved, which means that your guess was correct, taking into account that V is chosen as follows. So, I mean, quite quick. My main point is that the way that the solution for the QR will be derived is by guessing what the optimal cost is, parameterized with respect to a matrix V, plug it into the Hamilton-Bellman equation, see if there is an appropriate choice of V such that the partial differential equation is satisfied, because if you know that it is satisfied, indeed, the J is the optimal cost to go. Turns out that if you choose V as the solution of this ordinary differential equation, that's indeed the case. And then the control is given by, surprise, surprise, linear feedback on the state. Now with a slightly different set of multiplications. So that's all I wanted to say about LQR. Main point is that you would solve it still through the lens of dynamic programming. Now it's a bit more complicated because we have to solve a partial differential equation. But once you make this guess, it's not actually too complicated. And the main takeaways are that the optimal cost is still quadratic, and the optimal control is still linear feedback on the state. In the notes, you find all the details. Instead, what I want to do is to focus more on applications of differential games. So the differential game formulation, so the formulation where you also have a player 2, is actually quite useful in a number of settings. There are a number of so-called pursue evasion games, so games similar to the homicidal chauffeur problem that I mentioned before. And are a broad set of problems that actually are the ones we're going to focus on, are referred to as reachability problems. And then there are also many other problems in economics and such that lead themselves quite well to the differential game formulation. But in this class, I want to focus a little bit on reachability analysis that you might have heard, maybe. So in reachability theory, we are interested in computing the so-called backward reachable set of a dynamical system. So this is the set of states such that the trajectories that start from this set are guaranteed to reach a given set at the final time, TF. So say that you specify a given set. The question is, if you start 1 minute in the past, what is the set of initial states such that you are guaranteed to land into the target set at the present time? So again, the reachable set, backward reachable set, is a set of states such that the trajectory that starts from this set can reach some given target set. Now, depending on how you interpret the target set that you want to reach, then you have different flavors of a backward reachability. In particular, the target set could be something that you want to avoid. So basically, you want to find the set of states that, because of an adversarial choice of controls by player 2, would lead to the avoidance set. Well, you want to then start outside of that set so that you're not guaranteed to hit an obstacle, for example. So this will be the case of an avoidance set. So the target set is basically this, when you hit a tree, and the blue shape will encapsulate all those states such that if you start here, no matter what you do, there is going to be a strategy for the player 2. For example, a fairly unfortunate sequence of wind gusts that, boom, will bring you into the avoidance set. Why is that useful for control? For example, for planning algorithms? Because then you formulate your planning algorithm such that you never start from states that are within here. But sometimes the target set actually has a more benign notion. It could be the set that you want to get into. In the case, we talk about goal-reaching problems. The backward reachable set now has the notion of the set of states such that no matter how player 2 is trying to screw us up, we can still reach that set. And so for planning purposes, you want to start inside here. So depending on how you interpret the target set, you may want to start as player 1, either inside or outside of it. Now then the question is, how do you compute these sets here depicted in blue? That's a problem of reachability analysis. That's a problem to which we will apply Hamilton-Jacobi-Isaacs argument. So let me just state the problem more formally here. We'll apply the machinery from this lecture to these problems next time. I will also have an interactive script that will allow us to play a little bit with these problems. So to recap, the backward reachable set indicates that the target set corresponds to danger, so we don't get there, is the set of states x bar such that there exists a player 2 strategy, so that no matter what we do as player 1, under the joint dynamics, we're going to hit the undesired target at the final time, which is time 0. Conversely, the goal-reaching formulation is, so with the goal-reachable set, RT, is the set of states such that no matter what player 2 is trying to do, there exists a control action as player 1 that I can enact, such that under the joint dynamics, I'm going to end up in that state. So I'm happy. So these are the 2 classes of problems that we're going to look at. So we'll see later, we'll see on Monday how to apply the techniques we discussed today. It will take about 20-25 minutes. But you see that this is actually quite useful. You can use it quite a bit in a variety of robotics applications to protect yourself from obstacles in sophisticated settings whereby you might have disturbances such as wind gas or other actors. Or you can apply it in the settings so that you have very strong guarantees that you're going to fulfill your objectives. So to wrap it up, I know that there are some pieces in this lecture that are a little bit harder than usual. That said, I think it should be clear to you. The only part that might be a bit sketchy is the part when we invert the minimax. If you are interested in knowing more about that part, either come to my office hours or have a look at the 2 references that I provided in the second slide. But it's cool stuff. I mean, you'll see that actually we'll be doing, I will be showing you some interesting examples with the interactive script that I actually posted on the course website. So if you're interested, start playing with it in Colab to just get an appreciation of these tools. All right, see you on Monday.